Hey, what's up, folks? So we are going to go ahead and talk about some gas laws notes here today. Um, Friendly reminder, you will absolutely need a calculator here. I mentioned this a couple days ago in class, but are going to start some calculations involving gases here. It's not going to be like stoichiometry part two in terms of how difficult the math is. It'll be more like density problems from way back in Unit 2, like in September. It feels like a lifetime ago. Um, so there'll be some calculations. They're not going to be super duper difficult or anything like that. But you will need to stay really organized, as I always encourage you to do. And you will need a calculator of some kind. Today, if you want to use the calculators on your phone, that's no big deal. But remember, when you get to any quiz or test situation where it's worth a grade, you will need a real calculator. So you might as well practice with one in the meantime. I do have my big bin of calculators up in the middle of my room on that brown table. So you can feel free to grab one of those if you need to. Okay? Well, let's go ahead and jump into things here. We're gonna look at Boyles' law and Charles' law today. So those are laws that describe gas behavior. So when you mess around with a variable like pressure or volume or temperature, what does that do to the other variables? How does that affect them? What kind of relationships do they have? That's what we're going to be looking at here today. Now, we do need to do a quick overview of the variables that are going to be involved. Some of them are going to be more familiar than others. So, for example, volume will be in liters. We're pretty used to that, okay? Capital L for our liters. Now, you will see milliliters at times because we use that in lab settings because we are working on a pretty small scale. But I'll also intentionally throw milliliters your way just to make sure you're not sleeping on your units and that you understand what you're doing. So just don't forget, if you're starting with milliliters and you want to convert to liters, go ahead and move that decimal over 3 spots to the left, and vice versa if you're starting with liters and you're trying to go to milliliters. So for example, if you had, 591 milliliters of some gas, you'd have to move that decimal that's right behind the number 1, 3 spots to the left, and that would equate to 0.591 liters, or whatever gas it is you're talking about. Okay? So just watch out for stuff like that. Now, pressure, that new idea we talked about a couple days ago in class, that will be in atmospheres, abbreviated with an ATM for atmospheres. We talked about how when you are on the surface of the Earth, you have an entire atmosphere worth of air sitting on top of you all of the time, and the force from all those gas particles of our atmosphere, we call that a pressure. Okay, so we generally experience 1 atmosphere of pressure wherever we are. Now, sea level, considered like a height of 0, is where you experience exactly 1.00 atmospheres of pressure. We are slightly above sea level here in Columbus, Ohio, so it's like 0.99, but we're just going to basically assume it's 1 atmosphere of pressure unless the problem states otherwise, regardless of where it takes place on Earth. But lots of those problems you'll see very different pressures because we're doing special circumstances. Anywho, temperature, this will be in Kelvin, so you may have heard this unit before. We talked about it a little bit back in Unit 3 in October. But that is the temperature we're going to use for gases. It's based on the absolute 0 scale. It's really similar to Celsius. All you have to do is just take your degrees Celsius, which you're used to, add 273, and you got your Kelvin. So 1 degree Celsius is the exact same size as 1 degree Kelvin. It's just Kelvin is 273 degrees ahead of Celsius in that way, where, for example, 100 degrees Celsius would be 373 degrees Kelvin. So just kind of watch out for that sort of thing. Most of the problems I give you, at least at first, will be in Celsius, and you need to remember to convert that to 273 degrees before you move on and actually start your calculations. Now, we're going to see this new format where we have 1s and 2s all over the place. So a 1 means the initial or beginning, and a 2 means the final or the ending. And let me show you a quick example here. So you may see something like this in a problem, or when I'm working on my entry keys where it says V1. What that really means is the initial volume of something, or the volume of something at the beginning. Or you could see something like T2, and so that would be the temperature at the end of the problem, or the final temperature if you want. So that's just the format we use to make things pretty simple and clear. So ones and twos, when they're like a little subscript right after a variable like volume, temperature, pressure, that's just referring to the beginning or end of the problem. And you'll see plenty of examples of that here coming up. Now, if we think about Boyle's law here, it talks to us, it explains the relationship between pressure and volume. So here we got this little kid, he's swimming all these cute little fish, blah, blah, blah. Is that Nemo right there? Who can say? But he's, he's snorkeling or whatever, and he blows bubbles, that kind of thing. Now, let's take a look at what would actually happen to those bubbles as they rise towards the surface. I had this cool YouTube video of this guy sitting on the bottom of a pool. So this guy right here, he's laying on the bottom of like a 12-foot pool. He's kind of a deep one. And he has his hands out and he waves them a little bit to sort of keep his body flat against the bottom. And what he's going to do is he's going to blow bubble rings. Okay, it's a pretty sweet trick. You're like, whoa, dude, I bet he's a vape god. Anyways, so we're going to see what happens to those rings as they rise to the surface of the pool. So check this out. It's actually pretty sweet. Yep. Okay, so he blows a ring. Well, look at that. So those are getting way bigger as they approach the surface of the pool. They're getting bigger and bigger. Boom, boom. Get a pretty sweet angle here from directly above him. Get like 3 or 4 rings at once. Oh yeah, that's a sweet one right there. Look at that. So you can see the rings are clearly getting way bigger as they approach the surface of the pool. So we talked some about pressure in the pool a couple of days ago where you're like, oh man, my ears really hurt if I dive down to the bottom of it. Let's think about what's going on here. So if this is you at the bottom of a pool, okay, here you are, you're happy, yay. Oh, are those supposed to be your arms or whatever? You guys know I can't draw. At the bottom of the pool, okay, what's sitting on top of you? A whole lot of water, okay? So that's a lot of pressure. Lots of pressure, okay? Now, the bubble, when you first blow a bubble here, okay, it's really small because it's under lots of pressure. But as that bubble approaches the surface and there's less and less water on top of it, it will grow. And so we see a perfect example of this relationship between pressure and volume. So the volume of the gas, according to Boyle's law, decreases as the external pressure increases. So as the pressure gets less and less as the bubble rises towards the top of the pool, we should see, or I'm sorry, I said that backwards here. So as pressure increases, so at the bottom of the pool where the pressure is the highest, the volume of the gas is smallest, and exact opposite is true. So as that pressure decreases, as that bubble rises to the surface, when there's less and less water on top of it, there's less pressure, the volume increases. So those bubbles, they will get bigger as they reach the surface there. There's little you at the bottom. Look how happy you are. And so we see this relationship between pressure and volume. We call this an inverse relationship because they always do the opposite. So as pressure goes up, that means volume goes down. And as pressure goes down, that means volume goes up. Okay, so these two always do the opposite. In the density equation, it's sort of like how mass and volume have inverse relationships. You guys kind of remember that. If not, you can just ignore what I just said and just focus on this new stuff here. Here is the equation for Boyle's law. P1V1, and again, that means the initial pressure and the initial volume. So if you multiply the pressure times the volume at the beginning of a problem, then those should equal the pressure at the end, that's P2, times the volume at the end, volume 2. Okay? So P1 times V1 equals P2 times V2. So if you're ever given 3 of those variables, so let's say you know P1, V1, and P2, you should be able to solve for V2 no problem using your basic algebra skills. So that's kind of Boyle's law there. Now we got to talk about Charles' law, and one of the easiest ways to sort of show this is dealing with like hot air balloons. So what we have here is this lady. She's kind of there's a hot air balloon right next to her that's on its side, and there's a flame in the middle of that video, and you'll hear it here in a second. It's kind of loud when I turn it on. That flame is used to heat up all the air inside of the balloon. Okay, so the temperature is rising inside of that balloon. You can kind of see what happens to the gas inside that balloon here. Here we go. So the balloon started by laying on its side there. The camera will sort of zoom back out here in a second. And notice what's happening is that balloon is starting to really fill up. It was kind of flat before, but as they heat it up, it's really starting to fill up with that gas. What we're really seeing there as the temperature goes up, and I don't know why they went side angle with the camera here for a second, but as the temperature of the gas inside that balloon goes up, the gas really expands and fills that whole entire hot air balloon up quite a bit. Little fun fact, after watching this video for the first time, I was like, oh man, I should take my wife on a hot air balloon date. That would be really fun and spontaneous. But then I found out it's like $300 plus. And I was like, yeah, that's not happening. Anywho, so if we're going to actually talk about Charles' law officially, as the temperature of a gas increases, we'll see the volume also increase. So this is not like pressure and volume's indirect relationship or inverse relationship. This is a direct relationship between temperature and volume where they will do the same thing together. So we will see a decrease and decrease go hand in hand as well. If you think about this, kind of makes sense. When you increase the temperature of gas particles, they move around a lot faster. That means they're going to be spraying out more and more, expanding, like we talked about a couple of days ago when I showed you guys that PET simulation. So with a hot air balloon, as the gas in the balloon is heated, it did expand or get bigger, okay? So we started off with this balloon where it was, this is your little basket, and, oh gosh, I don't even know how to draw this. Oh, wow. The balloon was kind of like sort of flat and sort of on side, and then afterwards, you heated it up. Man, my drawing's so bad. I hope the sub, please don't judge my drawing too much. I know it's really whack. And afterwards, the balloon was like, boom, and it was way bigger, that kind of thing, because as the temperature of a gas increases, so does its volume. So we would say, hey, temperature goes up, volume goes up, temperature goes down, volume goes down. And that brings us to our equation ultimately here, okay, where we have V1, that is the original volume, divided by T1, that's the original temperature. And real quick, let's remember that volume should be in liters. And that temperature should be in what? What was it? The weird one? Kelvin, yeah. So if you take the original volume and you divide it by the original temperature, that should equal the final volume in liters divided by the final temperature in Kelvin. So again, just like the last one, if you have 3 of those 4 variables given to you, you should be able to find the 4th one without too much problem. So now the best way to solve this one, okay, is to do a little bit of cross multiplication, okay? So you're going to see stuff like this on answer keys where you'll multiply your T1 times your V2 and your V1 times your T2. You don't have to write those blue arrows on your nice little equation you just wrote there. But that will be a key way to solve a lot of these problems here. Now, before we get any further, I would like to point out that I do have a great spot on the back of your periodic tables to draw or to write all these equations. So substitute, if you wouldn't mind pausing the video here for about 60 seconds. Students, what you should do is you should get out your periodic tables and you should write Boyles and Charles' laws on the back of there so that you always have them for any quiz, okay? So if I were you, I would go ahead and write my Charles law where I'm like, okay, hey, P1 V1 equals P2 V2. And then we have our V1 over T1, Charles law, equals V2 over T2. Just like that. And that way you'll always have them ready to roll. Remember, in this class, I don't care that much if you have equations memorized. I think you often do memorize them because you use them so much. But to me, it's much more important that you know how to use them and what to do and how to interpret data and plug it into your equation. So anyways, now you'll kind of notice as we go through the rest of this unit, we're going to start filling in the rest of this section on your periodic table there, the combined gas law, ideal gas law, standard temperature and pressure, STP. We're going to get to all of those. And as we do that, you are going to want to kind of take a look at the back of your periodic table, start filling it out, make your life easier so you have all these equations in one spot. Okay? Anywho, let's go ahead and get to our worksheet here. So, substitute teacher, if you wouldn't mind pausing the video here in a second so that you can hand out this worksheet. You will have a quiz, students, over this on Friday. And you will need a real calculator by then. You can't use your phone calculator. So go ahead and pause real quick, sub, and then I'm going to go over the first couple of problems for the students to follow along. Okay, so now that you guys all have this worksheet here, let's go ahead and take a look at how to do the first couple of problems here. So as I'm reading through this, sometimes I kind of like to highlight or underline information that I deem important, especially when I get to like a number of some kind. So it says the temperature inside my refrigerator is about 4 degrees Celsius. All right, noted. If I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius, got it, and a volume of 0.5 liters, okay, what will be the volume of the balloon when it is fully cooled by my refrigerator? So what this is looking for here is that final volume. So the volume at the end. So it's kind of looking for V2. That's what we want to find here. Now, here's a good habit to get into. Before I do any calculations, I'm going to convert anything that I need to. So we're used to doing this with milliliters in the past. But the two things I got to convert right away are my Celsius here. So it says the temperature inside my refrigerator. Is that going to be my temperature 1 or my temperature 2? Well, if you think about it, if I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius, okay, so the initial temperature is 22 degrees Celsius. So T1 is going to be equal to 22 plus 273. So we got to convert it into Kelvin. So that would be 295. And T2, that final temperature, after the balloon's been in the refrigerator for a while, that's going to be 4 plus 273. And so we're looking at 277 for my T2. Okay, so the law we're dealing with here, which one has temperature and volume? Oh, that would be good old Charles' law, that second one we learned about. So we're using this equation here. V1 over T1 is equal to V2 over T2. So I'm going to go ahead and start plugging things in. So what was my original volume? It tells me it was 0.5 liters, that balloon, before I put it into the fridge and I did anything at the start of the problem. So I'm going to put 0.5 right there. My T1, well, that is 22 degrees Celsius, but I had to convert that to my Kelvin. So it's actually 295. My V2, that's what I don't know, so I'll just leave that as V2 for now. I don't know what else to do there. And my T2 is that temperature of the fridge at the end of the problem. So that's going to be 277. Now, what I need to do here is the easiest way would be to cross multiply. So I'm going to take 0.5 times 277. So that will get me 138.5. And then I'm going to do 295 times my volume 2, my volume at the end. And that'll just be 295 V2 times volume 2, the volume at the end. And a lot of times I like to put these in parentheses to keep them nice and separate. So what do I do to both sides here to get volume by itself? Well, what's the opposite of multiplying by 295? That would be divided by 295. So over here, these guys will cancel out. And over here, if I take 138.5 divided by 295, that should tell me what volume 2 is, my final volume. And if I plug that into my calculator, I'll find that's a little bit less than 0.5, 0.47. And what are the units on that supposed to be? Let me think. Okay, so it's a volume. All right, so that would be liters, capital L. And of course, I'm a model student, so I box that up for sure. In general, you'll see that I just kind of keep a couple of sig figs after the decimal. So 0.47, I don't need to go anywhere beyond that. So just make sure you kind of give me a couple of sig figs. So remember, those first couple after the decimal are zeros. Keep going until you get a couple of regular 1 through 9 numbers. All right, so that's the first one. Let's take a look at another one here. Synthetic diamonds can be manufactured at pressures of 60,000 atmospheres. That's true, actually. The way to get a diamond in is to put it under extreme pressure and temperature. If we took 2.00 liters of gas at 1.00 atmospheres and compressed it to a pressure of 60,000 atmospheres, what would the volume of that gas be? Okay, well, let me see here. So I've got 2 liters, that's at a pressure of 1 atmosphere and compress it to a pressure of 60,000. Okay, so I start with 2 liters of gas. It was at 1 atmosphere of pressure, and then I increased that pressure all the way up to 60,000. And then again, looks like we're looking for, what would the volume be? So we're looking for V2 again, final volume. That's what we need to get. So this is an example of Boyles' law where we have that relationship between pressure and volume. So we will be using this equation right here, P1 V1 equals P2 times V2. I'm going to go ahead and write out all my variables here just so I don't get them all mixed up. So my P1, my initial pressure, that's going to be my 1.00 atmospheres. My P2, that's going to be 60,000. Okay, so that's the increased pressure that we're putting on this sample here. My V1, my original volume, that is going to be the 2.00 liters. And my V2, that's what I'm being asked about. I don't know what that is, so I'm just going to go ahead and put a question mark. And look how organized I'm being. I have all my variables written out before I've actually tried to do any calculations. It's good practice there, and you'll see that all over my answer keys. Especially as we're starting out, I think a lot of you guys don't necessarily need that organization to get most problems right, but it's a good habit to be, and really early on, it's a very good habit to have before you sort of find a groove and you get used to these types of problems. So that means I'm going to take that original volume and pressure, I'm going to multiply them. So I got 2 times 1 there, and then I'm going to go ahead and set that equal to my final pressure of 60,000 times my final volume, which I don't know. Now, what can I do to both sides to get final volume by itself? Well, over here, if I divide by 60,000, that will cancel these out. I forgot 0 there. That will cancel these out and get volume, the final volume by itself. So I need to take 2 times 1 and divide that by 60,000 as well. This is going to get us a tiny number, and that's why it's important that we have 2 sig figs after the decimal. If you plug this into your calculator, you should get 0.000033. And again, what are the units? There should be liters. There we go. So we want to make sure that we are being very organized. We don't mix up our units. We always know what unit we're looking for before we actually start our calculations, so we can kind of pick our spot and move right towards the goal there. You guys have the rest of the period to work on this worksheet. The answer keys are up on my brown desk. You should be able to find them labeled. Substitute teacher, whoever you are, just an FYI, I always give out the answer keys on my worksheets, so that way students can kind of do a couple and check a couple, self-assess. In my classes, what I usually have them do, this isn't for a grade or anything, this worksheet I mean, and they can take those worksheets with them. That's why I have them a whole bunch and everything. So if you see a few students walk out with answer keys, no need to panic. Students, I know you guys know the drill. So go ahead and get work on this. Feel free to work with a partner. As long as you are quiet and behave well for my sub, we are all good. I will be back tomorrow, folks, because I'm not sick. I just have that doctor's appointment. So I will see you next time. Have a good one.